Hey everyone, welcome to The Explainer. So today we're looking at something so profoundly common that you've probably got 3 or 4 of them within a 30-foot radius right now. I'm talking about a tool that literally holds half of your house, your car, and your electronics together. We're tracing the journey of the humble screwdriver, from the blood and mud of medieval battlefields all the way to the hyper-exacting microscopic physics of modern industrial engineering. It's honestly an incredible story of human innovation.
Okay, let's dive into this. It's pretty easy to just look at a screwdriver in your kitchen drawer and assume it was, I don't know, spontaneously invented one day when someone needed to hang a picture frame. But the reality is that this common tool is the result of centuries of technological collisions, world wars, and manufacturing revolutions. To truly appreciate this everyday object, we kind of have to rethink everything we know about it and start at the very beginning of the screw itself. Here's our roadmap for today's explainer. We're going to start with the history of the screwdriver, move on to the battle of the bits, explore the science of soft handles, look at safety under high voltage, and finally, wrap things up with the physics of preload force. Let's get to it. Section 1. History of the screwdriver. From pumps to production. To really understand this tool, we got to rewind the clock way back, long before mass production, to see the surprising and literal twists and turns of its origins. The basic concept, an inclined plane spiraling around a central shaft, is actually ancient. We're talking ancient Greece. Archimedes didn't invent a fastener, though. He literally invented a giant wooden corkscrew to pump water vertically out of ships. Then, during the Hellenistic period, that same basic corkscrew design got flipped upside down to crush grapes and olives. But it wasn't until around the 15th century that it actually became a fastener. Back then, early screws were custom-made just to secure medieval jousting armor and early firearms. The tools were called turn screws, and everyday folks, they didn't use them at all. Fast forward to 1760, the English Wyatt brothers patented a machine that used a file to cut threads following a lead screw. That was a real game changer because it made mass production possible, basically paving the way for the tool we all know today. Section 2. The Battle of the Bits. Industrial Solutions. As the Industrial Revolution really kicked into high gear, mass production demanded faster, much more reliable assembly. This sparked a massive engineering rivalry in the 20th century over, of all things, the very tip of our tool. Now, what's really interesting here is the totally contrasting philosophies between these two massive innovations. In 1908, a Canadian named P.L. Robertson invented the square drive screw. His main goal? Absolute grip. The square shape meant the driver would basically never slip out of the head during installation. But then, fast forward 28 years to 1936, and Henry Phillips breaks onto the scene with a completely different idea. The Phillips cross-shaped design was intentionally engineered to slip out, or cam out, once the screw was firmly in place. This deliberate slippage was literally designed to stop early automated machinery from over-tightening and snapping the fastener. To give you an idea of just how crucial this bit technology was to early manufacturing, consider this number. Henry Ford, a guy absolutely obsessed with assembly line efficiency, was a massive early fan of the non-slip Robertson design. In fact, he used over 700 of those Robertson screws in just a single Model T car. But, as industry kept evolving, so did the need for serious torque. Enter the Torx driver in 1967. This design brilliantly married the best of previous ideas. It features a 6-lobe star shape that massively increases the contact surface area between the bit and the screw. This means it can handle incredibly high torque while drastically cutting down on that Phillips-style cam out. The Torx was such a huge hit that it sparked a whole new category of security fasteners. It eventually evolved into proprietary shapes, like Apple's Pentalobe from 2009. You've probably seen that one if you've ever squinted at the bottom of your smartphone. Moving on to Section 3, Science of Soft Handles, two-shot molding. Okay, we've all been there, right? You grab a cheap tool and the plastic handle just crumbles under pressure, or the grip starts peeling off after a few months. It's the worst. Solving this required a really clever manufacturing technique called two-shot injection molding. Premium handles aren't just one block of plastic. Let's see how this builds. Step 1. They inject a super strong, glass-filled nylon core into the bottom cavity of a mold, often called the A side. This gives the handle its rigid strength and keeps it lightweight. Then, step 2 happens almost instantly. A vertical injection unit shoots a layer of thermoplastic elastomer, or TPE, right over that nylon core in the B side top cavity. That TPE is what gives premium tools that amazing, comfortable, soft touch feel. Now, the absolute crucial takeaway here is the bond itself. By molding these two distinct materials together super fast, engineers create both a chemical and a mechanical bond. It's like they become one solid piece. This means the soft grip won't just peel away from the hard core, even if you beat it up on a job site. This kind of durability is a real game changer for long-term cost savings and reliability. And that is absolutely vital when these handles are integrated into high-tech electronics, heavy industrial gear, or critical medical devices where a failure is simply not an option. Section 4. Safety under high voltage, IEC 60900.
In certain extreme environments, this everyday tool transcends being just a piece of metal and becomes a literal life-saving device. When electricians are working in power plants, substations, or even on live low-voltage lighting networks, they rely on tools certified to extreme safety standards. Notice the really thick, heavy-duty orange PVC insulation on the tool handles. That is definitely not just for comfort. It's a critical protective barrier between the operator and potentially lethal electrical currents. To get certified for work on lines up to 1,000 volts, these tools are rigorously tested at 10,000 volts. That's a 10-times safety factor just to ensure absolutely zero dielectric penetration. Pretty wild, right?
The international standard governing all of this is IEC 6900. And let me tell you, the rules for working under high voltage are totally unforgiving. First off, you never touch live items directly. Always use a voltage tester first. Things like insulating floors and safety shoes are highly recommended, and obviously, you must avoid water at all costs. But most importantly for our tools, if you ever spot pores, fissures, or even see the white underlying insulation layer peeking through that orange PVC, you have to toss the tool immediately, no exceptions. Its life-saving capacity is completely compromised at that point. And finally, Section 5, Physics of Preload Force, the ultimate goal. All right, now we arrive at our final and honestly most technical stage of this explainer, the invisible physics of fastening. In modern mass assembly, just turning a screw until it feels tight just doesn't cut it anymore. The ultimate goal of any screw driving process is to generate what engineers call preload force. This is a very precise, defined holding power that keeps a joint securely together. It perfectly balances the connection so it doesn't fail, while making sure the allowable load of the screw itself is never exceeded. But here's the massive headache for industrial assembly lines. You literally cannot easily or practically measure this preload force directly while parts are zipping down a fast-paced factory floor. So what does this all mean? Think about this for a second. If you're manufacturing thousands of engines or smartphones and you absolutely must guarantee a perfect connection on every single screw, but you can't measure the actual clamping force directly, how on earth do you guarantee the product doesn't just fall apart? Well, this brilliantly illustrates the engineering solution. Because measuring tension directly is just way too complicated for mass production, engineers use indirect measurements. They measure the tightening torque, which is basically the rotational force applied to the head. Then, using some pretty complex math, like the VDI 2230 formula, they factor in the highly variable influence of friction. We're talking friction in the threads and right under the screw head. By balancing torque and friction, they can infer that ultimate target, the perfect preload force. It is a crazy, highly calculated balancing act of rotational power and material resistance. But, fastening isn't always just about cranking things down forever. Modern automated systems also have to handle realignment and disassembly procedures. Take electrical terminal connectors, for example. A machine will drive the clamping screw down to a predefined torque just to make sure it's fully seated, but then it'll precisely unscrew it to an exact angle measurement. This automated backing out creates literally just enough space for an operator to easily slide a wire in later down the assembly line. It's absolute precision control on a rotational axis. From drawing water out of ancient ships to securing medieval jousting armor, all the way to the automated calculation of torque and friction in modern manufacturing, the screwdriver really is a masterpiece of continuous human evolution. Which leaves us with a pretty fascinating question. As our materials get stronger and our electronics get microscopic, have we finally reached the absolute peak of this tool's design? Or will the friction of the future require an entirely new tool waiting just around the corner? Thanks so much for joining me on this explainer. Keep learning, keep questioning, and I'll see you next time.